Hello my dear students, I am Suhasini. Welcome back to my channel Learn with Suhasini Shinde. In the very last class we studied about the distribution of the charges, right? Continuous distribution of the charges. There were three distribution of the charge. One was sheet charge distribution, another was the line charge distribution and the volume charge distribution. We have seen the derivation for all the three distribution of the charges, right? And today's class we'll be learning about the electric field lines and the properties of the electric field lines, right? Now let us start discussing about what does the electric field lines means. You know, whenever I said you there is a charge, there are always lines around it, right? Now these lines are called as imaginary lines, right? These imaginary lines around the electric charge, the charge could be either positive or the charge could be either negative. Any region or the region around the any of the charge is called represent as electric field lines, right? If at all any other object coming into this particular field or the region will experience force and start moving into the direction in which the electric field is, right? Now the definition of the electric field is defined as electric lines of force is an imaginary line along which unit positive charge move when placed in it, right? Now these are the imaginary force line in which when a unit positive charge is placed, why do we say unit positive charge? It is a test charge, right? Test charge will be always unit and positive in nature. This test charge is always used to determine the impact of the force or the intensity around this region, right, due to this particular charge, say Q, right? And hence it says electric line of force is an imaginary line along which a unit positive charge move when placed in it, right? The unit positive charge starts moving into the same direction in which the electric field is there, right? Is this clear? Right. Now you have different types of the properties for this electric field lines. You have different types of the properties, right? Now let us see one by one. Now here the very first property of this electric field line is electric line always starts from positive and ends on negative. What does this mean? It means whenever you have a positive charge, right, the electric field lines always start from the positive, right? All the field lines from the positive charge are moving outwards, right? On the similar lines, when there is a negative charge, all the field lines will be intersecting or converging at the point of negative charge, right? Then what does it mean? Whenever you have positive and negative, all the charge lines, that is field lines, starts from positive and ends on negative. Start from positive and end on negative. Whenever there is positive charge, the lines are moving outwards, and whenever there is negative charge, the line are moving into the charge, right? And hence the first property says electric line starts from positive and ends on the negative, right? Next line. That is next property. Electric field lines never intersect. The electric field lines will never mix up together, right? They always move parallelly and they never intersect at any particular point, right? This is the main important property of the electric field lines, right? That electric field lines never intersect at any of the point, right? Next is electric field lines are purely geometrical and have no physical existence. We haven't seen how the electric field lines are moving, whether it is moving like this, whether it is moving outwards or whether it is moving inwards. These electric field lines are purely imaginary and it is a representation of some geometrical figures, right? And hence it is purely imaginary and it has no any pure or it has no any physical existence, right? Next. Tangent drawn gives the direction of electric field. See, electric field lines are very smooth curve, right? Wherever you wherever you feel electric lines, it is a smooth curve. It can be moving in this direction, it can be moving into this direction, right? Now say this is the electric field moving into this. This is the electric field moving into this direction. At any point on this particular electric field lines, if you draw a tangent, then it represents the direction of the electric field. Say for example, now you have this point. Now you drew a tangent here, right? If at all you drew a tangent here, now this particular arrow will be representing the direction of the electric field for this particular field line. Is this clear? Now if at all you have another point here, right? Now you drew a tangent like this. Now this tangent represents the direction of the electric field for this particular electric field line, right? So what does the property says? Tangent gives the direction of the electric field. Any point you drew a tangent on the electric field line, it gives the proper direction in which the electric field is moving, right? This is the next property. Now electric field lines repel when there are like charges and attract when there are unlike charges, right? Say for example, you have kept both positive charge. Any lines that are being present, or any lines, electric field lines that are developed in between these two charges are repelling from one another, right? This is going apart, this is going apart, right? Both the field lines are moving apart due to are repelling each other due to the like presentation of the like charges, right? Okay, you can see here in the very next case, whenever you have two different charges, that is positive and negative, the electric field lines from positive are starting and it is converging towards the negative. All the electric field lines are away from it and all the electric field lines are into the negative charge, right? Here the presentation of the electric field lines makes you understand the attraction of the electric field lines whenever there are unlike charges exist, right? There is difference between these field lines and these field lines. Here whenever there are like charges, the electric field lines repel from each other, and whenever you have unlike charges, the electric field lines attract each other. Is this proper? Right? Next, electric field lines are crowded in the strong electric field and spread out in the weaker field. Whenever there are so many crowded lines or the electric field lines, then it gives the indication of the strong electric field. And whenever you have a very say spread out kind of the electric field lines, then it is a symbol of the weaker electric field. For example, you can understand like this. Say you have electric field lines here, right? And you have electric field lines here, right? Now these are the electric field lines, right? Whenever the electric field lines are crowded in some particular region, this particular section represents a strong electric field. And whenever there are a spread out kind of the electric field line, now this represents the weaker field, right? And hence it says electric field lines are crowded and it is strong electric field. Whenever it is spread out, it is represents the weaker electric field. Is this property clear? Right? Next. If electric fields are parallel equispaced, then it represents the uniform electric field. If the electric field lines are parallel to one another and they are equally distanced from one another, then that particular region you call it as a uniform electric field. And the converse of it, if at all they are not parallel to each other and they are just moving randomly with improper distance between one another, then it is non-uniform electric field, right? This is the one property of electric field lines. Now next is electric field line never enter conductor. That is electric field intensity inside it will be always zero. I said you in the very last class, if you could remember, whenever I say charge on any particular body, the charges are always segregated around or segregated outside the surface area, right? If at all you have a cylinder, then the charges will be outside the surface area. If at all you have circle or the sphere, the charges will be spread out outside the surface area, right? Now what does this mean? Electric field lines are present only whenever there is electric charges, but the charges are present outside the surface area, and hence there is no electric field line or electric field intensity that exists inside the conductor. So whenever you have a conductor, the charges are located outside the surface, and inside the conductor electric field intensity will always be equal to 0. Right? This is also a very important property. Now electric field lines are perpendicular to the surface of the conductor. Now as the charges are segregated or deposited on the surface area, and hence every electric field lines will be perpendicular to that particular surface of the conductor, right? Now these are all the important properties of the electric field lines that you have to understand. Okay, next we'll be studying about the electric dipole. What do you mean by electric dipole? Electric dipole is a set of two equal and opposite charges with a very small distance between them, right? What do you mean by this? It has two equal and opposite charges. What do you mean by equal? Equal in their magnitude, right? If at all say it is 3 microcoulomb, right, and you also have another charge that is opposite to this, which also has 3 microcoulomb of magnitude and a very small separation of distance between them, right? Now what do you mean by dipole? A dipole itself indicates two words in it. Di is what? Two. Pole is different polarity, that is different polarities, right? Electric dipole. An electric dipole is a set of two equal charges with the opposite, right, with the opposite polarity and a very small distance separated between them. or whenever I explain about the electric dipole, four important terms come into picture, right? The very first is dipole moment. What do you mean by dipole moment? Now this dipole moment is indicated by P. Now this is P will be equal to, dipole moment is equal to distance between the charges and magnitude of any one charge, right? 2a is the distance between the charges, and q a magnitude of any one charge. Why? Because both are same magnitude, right? The distance between the two charges is 2a and the magnitude of one is q, right? The product of the charge and the distance between them represent this dipole moment, right? Now this dipole moment gives the strength of the electric field that is generated due to this electric dipoles, right? Now whenever you calculate dipole moment, then what do you calculate? You calculate the strength of the electric field that is created by this electric dipoles. It is called as dipole moment, right? Next is axis of the dipole. Now what do you mean by axis of dipole? Axis of dipole is the line joining between the two dipoles. The line joining the positive and the negative charge, this particular line is called as axis of dipole, right? Now what is axial length, right? Any line that is passing from this particular point, this can be a axial line, right? Now the axial line could be drawn for wherever a distance it is. It can be drawn from wherever distance it is, but it should pass through the center of the two dipoles, right? This is called as axial line, right? Now what is equatorial line? Now what do you mean by equatorial line? Equatorial line is a line drawn perpendicular at the center of the dipole, then it is called as equatorial line. Now did you understand what dipole moment, axis of the dipole, axial line and equatorial line, right? Now these all four terms are very important when you deal with the electric dipole, right? Now the very main concept of studying this electric dipole are, there are two main concepts of studying this electric dipole. You want to understand what is the electric field at some particular point due to the electric dipole, right? There are two concepts which come into picture whenever we deal with the electric dipole, that are, see, you have this point that is positive charge, you have another charge that is negative. These are dipole now. Now this is an axial line. On this axial line, wherever the point is, whether you say the point is P here or the say point P is here, wherever the point is present on this particular axial line, what is the electric field induced or what is the electric field influenced on this particular point due to the dipole is determined in one condition. This is first condition to find out what is the electric field at a point on the when the point is placed on the axial line, right? This is the first condition. The very second condition into it is, this is positive, this is negative, you have an axial line here, right? You have another line called as equatorial line. If at all the charge or if at all the point is present on this particular equatorial line, then what is the electric field at that particular point due to these dipole is being calculated. There are two conditions. One point on the axial line, another the point on the equatorial line. These two conditions form an important condition for the electric dipole. Now let us learn one by one. When electric field, what is the electric field at a point P due to when it is kept on the axial line, and in the next derivation, what is the electric field at a point some P, say the point could be here, it could be here, right, when kept on the equatorial line. Is this clear up to this point? Okay, in this derivation, let us understand what is the electric field at a point when it is kept at some axial length, right? Now there are dipoles. Dipoles means two opposite and equal charges with some distance between them, right? Now this is the positive charge and this is the negative charge. Now these two charges forms dipole, right? Now what is the distance between these two? It is 2a, right? And exactly counted when at the center, it is a and a, right? Now you are able to understand why it is 2a, right? The distance between both the point is 2a and exactly at the center it is a and a, right? You have another point on this axial line. Axial line is this line, right? At some particular point P, you will find out what is the electric field intensity at point P due to the positive charge and also due to the negative charge. right? Okay. Now I have written the derivations completely so that it doesn't take me much time to derive and write and all the things, right? Once it is written properly, then I'll explain step by step, and every notation and every derivation, every step is like explained very clearly. You have a point here P. You want to find out what is the electric field due to these dipoles here. The very first point is, now this will be experiencing some electric field due to the positive charge Q, right? Now first you write down what is the electric field due to some particular point charge. Now in the very last classes we have derived the expression for electric field or electric field intensity due to one particular point charge. What was it? It was E is equal to 1 divided by 4 pi epsilon naught Q divided by R square. Do you remember this formula that we have explained? We have derived in the last class, right? The exactly same is being taken here. Now electric field due to positive charge Q at a point P will be equal to E is equal to due to positive 1 divided by 4 pi epsilon Q. This Q is this positive Q, right? Divided by R square. What does this mean? R minus A square. That is a distance between that particular point and the location, right? Okay, what is the distance between these two? It can be got R minus A, then we'll get this particular distance. So it is R minus A whole square. That is R minus A square. That is R square, right? Now next, electric field due to minus Q at P. Now you have another electric field due to this particular charge Q, that is minus Q. What is that again? E minus Q will be equal to 1 divided by 4 pi epsilon naught. It is minus Q, right, divided by what is the distance between this point and this point. How can we write the distance between this? You can add this thing R and A. R plus A will be the distance between P and minus Q, right? It is R plus A whole square, right? Next, now the total electric field at particular point P will be equal to the vector sum of both the electric fields, right? So it is E is equal to EQ plus E minus of Q. Now you just add both the things. This is again same written, 1 divided by 4 pi epsilon Q divided by R minus A whole square. This is for A Q, and 1 divided by 4 pi epsilon minus Q R plus A whole square. This is for minus Q, right? Both you add. Now this is the further is all the mathematical derivation. There is nothing concept or application here, right? This is purely maths now. Now you just follow this 1 by 4 pi epsilon and Q. Both the terms it has Q, you take it common. So 1 divided by 4 pi epsilon naught into Q, right? What is remaining here? 1 divided by R minus A whole square minus 1 divided by R plus A whole square, right? This is remaining. Now next further you take the LCM. After taking LCM again you write the same things, 1 divided by 4 pi epsilon naught into Q. After taking the LCM, this R plus A whole square will come here, R minus A whole square will go there, right? Now you define this, or you can you simplify this particular equation. What you get? E is equal to 1 divided by 4 pi epsilon Q is as it is. R plus A whole square is A plus B whole square. What is A plus B whole square? A square plus B square plus 2AB. This is A minus B whole square. It is A square plus B square minus 2AB. This is extended here. A square B square plus 2AB minus, this minus sign is kept as it is, minus A square plus B square minus 2AB, right? You again simplify this. Q by 4 pi epsilon naught. You take out this R, same as it is, R square A square plus 2AR minus R square plus into minus minus A square minus into minus plus 2AR to that of R minus A R plus A whole square, right? Now this, why this denominator here it is, you have R minus A whole square, R plus A whole square. You can write it, taking the square outside, you can write R minus A R plus A whole square, right? Now what are the terms that cancel out? R square plus R square minus R square cancel out, right? Plus A square minus A square get cancel out. What we have left out with now? 2AR plus 2AR. 2AR plus 2AR is equal to 4AR, right? That will be written further, Q divided by 4 pi epsilon naught, 4AR, right? And this R minus A, R plus A whole square is this again the mathematical formula, right? It can be written as A square minus B square, right? What is the formula for the A square minus B square? It is A plus B and A minus B. It is the same. A square minus B square is A plus B and A minus B. And you have the whole square, so it is whole square here, right? Next, Q divided by 4 pi epsilon naught. Now this 4 can be written as 2 into 2, right? 2 into 2. This is written further here. 2 into 2. Right? Now why do you write this 2 into 2 is, you know what electric dipole is. We have understood what electric dipole in the very previously. Electric dipole will be equal to the distance between the two charges and magnitude of 1. Right? This represents the electric dipole. So this can be easily put here. So we split this 4 into 2 into 2. Right? So now this 2 into 2a QR. Exactly the same things is written here. Now this represent the dipole moment P. Right? So that is put again here. That is 1 divided by 4 pi epsilon naught. 2, that is the same 2. Right? Now this Q, this 2a is represented P, that is dipole moment, and the same R, and the same thing, R square minus A square whole square. Right? Now here you can understand where this P is called as 2a into Q. Right? Now this was the scalar form. Why do you call this equation as scalar form? Why? Because we haven't represent the directional vector into this expression. Whenever we put directional vector into some expression, then only the expression becomes a vector form. Until that point, it will be a scalar format of any expression, right? Now when you want to write the electric field, now this was the electric field, right, in the scalar form. When you want to write in the vector form, the same thing again. E is equal to 1 by 4 pi epsilon naught 2 PR divided by R square minus A square whole square into N. What is this N? Right? This is a unit positive directional vector whose value is 1. This is direction vector. This shows you what is the direction of the electric field at any point. Right? Next, now we have a condition. What if the distance between the point that is located and the center is so big that the distance between these two charges is so small? When the distance between the two charges is considered so small compared to that of the point that is located on the axial length, then what does this mean? This R square minus A square will be almost equal to R square only. Why? Because A square doesn't exist at all. What is A square? The distance between these 2 points. It is so small that can be neglected, and the only term that is remained is R square. So it is written, if at all, R, the distance between the point located and the center, if so large, then R square minus A square will become R square only. Why? Because this term is neglected because it is very small. Right? When this is the point, then what you write here, instead of writing this R square minus A square, this is neglected, you write only R square whole square. Right? So 1 divided by 4 pi epsilon naught 2 PR R square whole square, 2 2s are 4, it becomes R raised to 4. Is this clear up to this point? Okay. The final expression how you could write, now you have 1 R here, right? You have R raised to 4 and 1 R here. This can be cut, right? Now this becomes R cube, right? The total and the final electric field expression due to the electric dipole on a point located on the axial length will be this. That is, E is equal to 1 divided by 4 pi epsilon naught 2p divided by R cube into a directional vector N. Now this will be the total final expression for the electric field on the axial length due to the dipole. Is this understandable up to this particular point? Right? Now this was all about this derivation. Okay, this was about today's class, the derivation for the electric field due to a dipole along the axial length. In the very next class, what we'll be doing is, now we have found out what is the electric field on the axial length, right? Now in the next class, we will find out what is the electric field at any point on the equatorial line, right? We have a separate derivation for this particular. What is the electric field at any point on the equatorial line, right? This will be dealt in the very next class, right? Hope this is clear, right? And thanks for all my dear students for watching my videos and liking it, right? And the material for this particular chapter will be found in the description box. You can go and check out. And thank you one and all. So you please do subscribe and share my channel link with all the friends and families. And thank you so much.